115 kV, the next generation. How exciting. We'll talk about this very similar to the way I talked about the last 69, our objectives, approach, components, drawings, right-of-way optimization, and some other benefits, power quality improvements, and then we'll take a look at a pilot. The same exact objectives that we had with 69: improve reliability, power quality. We want to reduce the right-of-way. We want to allow additional circuits to be built in that existing right-of-way. We want to make it easier and faster to get approvals for new right-of-way or right-of-way expansion. Telling the Public Utility Commission you're going to, have a smaller right-of-way and have environmental stewardship and have a smaller carbon footprint is going to get you a quicker right-of-way permit. We want to preserve the environment. We want to minimize public relations issues due to line location, routing, design, EMF. We want to help utilities meet the goals for reliability. And environmental stewardship is stated in their strategic direction, mission, vision, and regulatory agency targets. And we want to obviously reduce vegetation removal, management, and trimming. As you're probably going to guess, the same exact design approach we have for 5, 15, 25, 35, 46, and 69. We're using the same 69 kV covered conductor for 115. Why? There's a lot of reasons. We don't want to use more material. It's getting heavy. We have more than sufficient 60 hertz withstand and BIL. The charging current on the jacket is acceptable. We don't want to increase the weight and increase the cost. The spacer is massively different, and the pole design specs, you've got to run your calculations and see what kind of pole you need. So again, the spacer is very different. We'll take a look at that. We're going, instead of 30 feet between spacers, now we're going 50 feet between spacers. We say 40 to 70. We're recommending 50. That spacer weight is no longer 2 pounds, a couple of pounds. It's more like 85 pounds. So that's getting heavy. The cable is the same cable we used at 69 kV. So we've been involved with testing this 115 kV system for as much as 15, 20 years. We did initial Corona concept testing on the spacer system, the assembly, the dead end, and the tangent. We did positive and negative impulse testing. We did power frequency dry and wet, flashover testing. We did RIV testing. And again, these are all according to standards, to our standards, since we don't have standards from ICEA or IEEE or ASTM yet. We did spacer, insulator, steep front impulse testing. We did tons of mechanical testing on the spacer, insulator, and the bracket. We did cable BIL, AC breakdown, and wet wood testing. And we did field testing on our pilot circuit every 3 months, probably for the last close to 4 years. So here's the spacer. The 15 kV spacer, it's about essentially the same size as the 25 kV spacer. You can see when I get to the 69 kV spacer, it's instead of 24 inches high, it's 63 inches high. Instead of 15 inches wide, it's 40 inches wide. When we go to the new 115 kV spacer, yes, it is quite a bit larger, 93 high and essentially 71 wide. Different ball game there at 115 kV. Here's some of the components. Don't want to get too down into the weeds. We're using a galvanized steel support bracket to maintain the separation. We're holding heavier phase conductors, and we're holding there's longer spans between the spacers, so they will be forced to hold more weight. We're using a messenger clamp with a shackle. A Y clevis allow bidirectional movement. We're using polyethylene clamp inserts between the spacer clamp and the cable itself to protect the cable covering, give us a higher BIL. And we're using a high voltage metal cable clamp for mechanical support. So that's what that spacer looks like.